So I'm going to record. I hope I'm recording the right screen because the last thing I want to do is record the. You can see these two pages,
Yep.
right? So I assume that's what I'm recording. So again, to start the class again, because I'm recording it now. Uh, it was known to Galileo and Newton that physics was the same whether you were standing on the earth or riding in a carriage. We call that Galilean or Newtonian relativity. What Einstein did was say, well, it doesn't matter how fast the carriage is going, physics looks the same as long as as long as it's not accelerating. And of course, as what was physics then was electrodynamics. And in fact, at about that time, namely about 120 years ago, um, various physicists, Poincaré and Lorentz, I guess, and some others, had shown that the equations of electrodynamics were invariant under transformations that are called Lorentz transformations. These are like rotations, but what's invariant the is not space squared plus time squared, is space squared minus c squared times time squared. Um, and what Einstein said was, well, the physics, namely electrodynamics, is the same in any Lorentz frame, in other words, in any frame without any acceleration. And what we now know that that's even truer than he did than people knew at the time that Einstein announced this, because at that time, 1905, the only thing that he could do was say, while riding in a train, a good Swiss train, it was possible to drink tea, and just as well as if you were in the train station. Now we know the Earth is moving at 370 kilometers per second in the direction of the constellation Leo, and that's an absolute speed relative to the cosmic microwave background radiation, the CMB. Um, and that speed of the Earth then is about 1% of the speed of light, which of course is 300,000 kilometers per second. And Michelson and Morley back in 1905, and actually it was earlier than that, they did their experiments in the 1800s. And in other words, the last couple of decades of the 19th century. And in fact, Michelson was actually in the Navy when he did his first experiment. Um, anyhow, uh, he showed that the speed of light was independent of direction, and in as much as when you change direction from parallel to the motion of the Earth to opposite direct, anti-parallel, you have a difference now of 2% of the speed of light, and that's way, way more than the maximum error that he allowed. I mean, he was able to measure the constancy of the speed of light to much better than 1%. Um, and of course, there are millions of experimental, or not millions, but there have been many experimental tests of, well, probably have been millions of experimental tests of special relativity, because all the accelerators are built using special relativity and they all work. One example, by the way, of special relativity that I find particularly striking is, I possibly find it striking because when I was a graduate student, one of the experiments that I was supposed to do was to measure the lifetime of the muon. And we didn't make muons, we just depended upon cosmic rays to hit nitrogen and oxygen atom nuclei in the upper atmosphere, 10 kilometers above us, and they would create showers of pions. The pions would decay into muons and neutrinos, and then the muon, some of the muons would go toward Earth. Let's see, if I go forward a little bit, maybe I can find the numbers a little better for this, the numbers for the muons. The muons would not make it all the way to Earth if it weren't for the fact that there's time dilation. So the time in the rest frame of a rapidly moving particle, time goes by more slowly. And this is kind of annoying that I can't find what I'm looking for. So let me just use the computer to find the thing. So muon, okay, there we are. Right, there's the example. So a muon at rest, for example, has a mean life of 2 microseconds. Cosmic rays hitting nitrogen and oxygen nuclei make pions high in the Earth's atmosphere. The pions rapidly decay into muons in 2.6 times 10 to the 8th seconds. That's the pion decay. So basically, the cosmic ray, a proton or whatever, hits a nucleus in the upper Earth's atmosphere and produces pions. The pions almost immediately become muons. And then some of the muons have to get to the ground. That's 10 kilometers. So at the very minimum, it's 3 times 10 to the minus fifth seconds to hit the ground. But the lifetime of the muon measured on the ground is 2 microseconds. So if it weren't for time dilation, the probability of a muon reaching the ground as a muon would be e to the minus 30 over 33 over 2.2. That's 2.6 times 10 to the minus 7. So in other words, you wouldn't see anything. And on the other hand, the mass of the muon is 105 MeV. And so a muon of energy 750 MeV has a time dilation factor of about 7. And the result is that the probability is 0.12. So about 12% of the muons survive and get to the, in the case that I was doing as a graduate student, we had just a big jug of paraffin, and the muon would stop and around one of the carbon or oxygen nuclei and decay, and we'd measure it. Anyhow, that's a striking demonstration of relativity, of one of the consequences of relativity. Let me get back to the, oh God, I went the wrong way. Hold on. On the class webpage, I put chapter 12 and chapter 13 PDFs of those two. And also I put this whole PDF of examples, but you'd want to go to chapter 12 of it. And here, for example, is the CMB radiation in the rest frame of the CMB. And up here, on the other hand, is what this would look like if the if we didn't correct for the Doppler shift due to the speed of the Earth, which again, 370 kilometers per second. In any event, the basic rule that Einstein discovered, the transformation of space and time that occurs, so that if you're in a rocket ship Well, for example, suppose you are in a rocket ship and you have front and back windows, and light comes in the back window, and um, the light is coming from another spaceship, and the spaceship might be, 100 times faster than your spaceship, and so you'd think without relativity that the speed of light would be faster if the light going was that way, or if on the other hand, that that if you were going toward the spaceship, um, or let's put it differently, you have the light coming in from a spaceship that's going at a certain speed, and you're going 100 times faster, but still slower than the speed of light. You'd expect the speed of light going through your spaceship would be slower, but it's not. It's the same speed. And if in fact you're going slower than the other spaceship, you'd think speed of light would be faster, but it's not. It's the same. So that means that electrodynamics is the same. And in order for it to be the same, what was worked out was that things would be fine if you just used coordinates in your spaceship that were related to the coordinates of the other spaceship by what's called a Lorentz transformation. Equivalently, you can say the quadratic separation between two infinitesimally separated points, I'm using P for point here rather than momentum, that differ by a little bit in time and space is ds squared, and that's the space distance squared minus c squared dt squared. And in the absence of gravity, then ds squared is the physical quadratic separation. And since it's physical, it can't depend on the coordinates. That's the basic idea, the basic physical idea. That is, but of course, it's the same as the idea of relativity, that the distance, that the separation is physical, and if it's physical, then it's coordinate independent. And so the changes of coordinates that leave this thing invariant are called Lorentz transformations, and they're 4x4 matrices. And so the way people write them is to use, for example, upper indices. So you say xi prime, where I can be 0, 1, 2, 3, 1, 2, or 3, is a sum over k from 0 to 3 of lik xk. Lik is just the ith row and the jth column of the Lorentz matrix. And what Einstein did, he got very tired of writing these summation symbols. And so he said, well, let's just agree that if we have one upper symbol and one lower symbol, and it's the same, we just sum over them from 0 to 3. And then the Minkowski matrix, that is the metric of flat space, is just this thing here. And you can then write ds squared as dx prime I, dx prime k. And if you write that out, you see that it is just this quantity here with just all primes, because I had all primes. And then it's got to be the same as this without the primes. And the relation is that the thing with the primes is related by the Lorentz matrix. And now if you compare these two equations and you strip away the dx's, you see that you've got to have a sum over I and a sum over k of LIL, eta IK, LKJ has to be eta LJ, where this eta is this thing here. So that algebra defines the basic rule for the basic matrix definition of a Lorentz transformation. That is to say, it's in terms of this 4x4 matrix, the Lorentz matrices have to satisfy this rule. And I think you've learned somewhere that, oh, we're almost out of time. Is there a question, perhaps?
No, none in particular.
All right. Okay. Well, if you look at you remember that the determinant of a product of matrices is the product of the determinants of the matrices. And the determinant of eta is -1. And so we get -1 is equal to -1 times the square of the determinant of L. So the determinant of a Lorentz matrix is ±1. And so it's a little bit like a rotation where the determinant of a rotation is always just 1. And but if you have a reflection, of course, it can be -1. But a rotation is just 1. So this is like a rotation, except for the fact that you get this minus sign in the time direction. Now, maybe I should say something about this matrix notation here. Left indices label rows, right indices label columns. Well, that's the way it always is with matrix notation. Transposition, when you take the transpose of a matrix, you interchange rows and columns. And so this equation here that defines a Lorentz transformation, you can write it, since you want to have the I next to the eta, you can do that by making the transpose here. So this, in matrix notation, this is L transpose eta, L is eta. So that's I find that much more friendly than this relation with the indices. In fact, the fewer indices you have, the nicer things are. And well, this just recapitulates some of what I was saying. Eta squared is the identity. Evidently, if you multiply this by itself, you just get 1. And so that means that eta squared, well, you take this equation, you multiply by eta, you get eta squared, which is the identity on the right-hand side. So then you have this times that, or rather this times that is 1. So this thing here has got to be the inverse. So eta transpose of a Lorentz matrix times eta is the inverse of a Lorentz matrix. Or equivalently, the transpose of the inverse is eta L eta. In terms of indices, it looks like that. Here's a representative Lorentz transformation, which is a boost in the one direction. And so you have Kosh and Cinch. And so it looks like this. If it were a rotation, you'd have a minus sign here, but there's no minus sign. And you'd have cosine and sine, not Kosh and Cinch. The thing that one wants as a student to keep, and as a working physicist to keep one's eye on, is the things that are invariant. So ds squared is invariant, but the inner product of any 2 4 vectors is Lorentz invariant. So the 4 vector here would be position or momentum. And I should have mentioned that actually in this description here. But in any event, the inner product of any 2 4 vectors is invariant. And as for physical points, if you have 2 physical points, P and Q, if you take their difference and then take the invariant length of their difference, you get the difference of the space squared minus the difference of the time squared. That's invariant. And so then we say, if it's positive, we say it's space-like because this term dominates. If it's negative, the time part dominates, we say it's time-like. And if it's 0, then the two are equal and it's light-like. So we're just about out of time. I I'll try in the next lecture to be a little more physical, I guess, and less mathematical. In any event, where we can, I think what I'll do is focus on electrodynamics and the invariance of electrodynamics and the various things that are invariant, because those are the things that you can calculate in one frame and then you know what it is in any other frame. If you have to actually compute how something changes, well, then it's 4x4 matrix multiplication. And well, that's trivial in MATLAB, but anything more than 2x2 is hard with your fingers. So, all right, well, I'll say goodbye now, and I'll hold class again on Tuesday, and we'll see if anybody comes. And I don't know how many students will need to register for the course to be official, but that's a decision made by the chairman and the administration. For a short course, he may go with 1 or 2 students. Anyway, I'm going to stop now. Have a nice weekend. Try to